This is Dr. Sweeney, and I wanted to welcome you to our very first video for Computer Science 140. This is discrete structures. For those of you who are not inside of the class, what we're going to be looking at is many topics inside of mathematics that directly have to do with computer science. The first one we're going to be looking at is the rules of logic. And what I've decided to do with logic is I've decided to kind of break it up into some component parts. This particular one is going to focus in on the rules of logic and the utilization of truth tables to ascertain truth about logical statements. So we're not actually going to be looking at what does it mean to be a conditional statement, what does and mean or mean when in English. We'll have a separate video on translating that will help you with that. In this case, we're just going to look at the rules of logic and how do we utilize those and how do we use them in order to do truth tables and to ascertain truth from symbolic logic. Okay, so we'll talk a little bit about meaning, but mostly we're going to be focusing on how do we determine truth utilizing this kind of symbolic logic. So we're going to start out in logic. We're going to start with these ideas called propositions. And what a proposition is it's a statement whose truth can be ascertained. Right? What does that mean? That means that we can either determine whether or not it's true or it's false. Okay? There are a lot of different statements inside of, any language, and not all of them are propositions. A proposition, in this case, is just something that we say, okay, here is X. Is it true? Is it false? We're not actually interested in whether or not it actually is true or false. Okay? Just that it can be proven to be true or it can be proven to be false. And that's what makes something a proposition. So we're generally going to utilize some letters. We're going to start with P, and we'll use Q, and we'll use R, but you can actually utilize anything to represent a proposition. All right, so like for example, the duck is black. True or false, right? That's a proposition. And so atomically, these are what we call the atoms of symbolic logic. That is that we start out with them, we ascertain their truth, and then they're going to be what we build off of. Now that we have our atoms, right, our basic building blocks for logic, we now want to get into our first compound proposition, and this is and. And we utilize this symbol right here for and, okay? And so what we're going to ask is we're going to have P and Q. We've got two propositions, two different ones, P and Q. And we want to determine when we know that P and Q is true. I don't really care what and means at this point. All that I care about is what are the rules that determine whether or not P and Q are true. So what I'm going to do is I'm going to generate a truth table, a set of rules of logic that determine for me when in fact P and Q are true. When P and Q is true, excuse me. So I've got P, I've got Q, and what I want to do now is and then this is called P and Q. And this is how we set up this thing called a truth table. It's got 4 slots because it turns out that we have 4 possibilities for combinations of P and Q. So we could have P be true and Q be true. We could have P be true and Q be false. We could have P be false and Q be true, or we could have both P and Q be false. Now, if it's the case that both P and Q are true, we've got true, true is what we say, then P and Q is true. If, on the other hand, Q is false, P is true, we're going to have false. If P is false and Q is true, we'll have false. And if P is false and Q is false, we're going to have false. These are the rules, okay? And it turns out that calling something P and calling something Q is completely arbitrary. When we get into logical equivalence a little bit later and proving things using logical equivalence, that order is going to matter somewhat. But for our purposes right now, whatever you call P, whatever Q actually is, whatever P actually is, it doesn't matter. All that matters, right, are these rules. And the rule here for and is that for and P and Q to be true, both P has to be true and Q has to be true. Our next compound proposition is or. And so we're going to have now P or Q. For P or Q, our truth table is going to look as follows. We'll have P and Q, those are our 2 propositions, and then our compound proposition P or Q. Then we'll have our 4 choices that we had exactly the same as they were before. So that's true, 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 false, false, true, and false, false. Then we want to determine when is P or Q going to be true. P or Q is going to be true when we've got true, true, that's going to be true. True, false is also going to be true. False, true is going to be true. And false, false is going to be, though, false. So in the case of or, what we've got here is we have that one or the other is true. Okay? Or both. So as long as one and only one of the or is true, we end up with a true statement with this particular or. Now this or, okay, is called an inclusive or because it actually indicates for us that we want to know we're going to assign truth for when both P and Q are true. We have a different or, which is called an exclusive or, that's going to be slightly different in terms of its truth table. Okay? And its truth table, it's going to see P or Q. Right? So same English word, but different idea. This one is going to assign, so we got true, 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 false, false, true, false, false for P and Q. And then P or Q. True, true is now going to be false. So in the case of the exclusive or, we can only have truth if one or the other of P and Q is true. So only one can be true. Otherwise, we have false. So notice the difference here between these two is in that first line. In the inclusive or, what we have is we have true, true gives me true. In the exclusive or, we're going to get true, true gives me false. The next important, basically symbolic logic statement is actually what we call a negation. Okay, and a negation, which is represented by basically looks like a sideways L, essentially means not. Okay, and a negation is pretty easy in terms of its truth table. Essentially, what we do if we have a negation is if we have P, then not P is going to be the exact opposite. So if P is true, then not P is false. And if P is false, then not P is true. Very simple, very straightforward. So what we're going to look at now is we're going to look at conditionals. And conditionals, they're actually kind of tricky when we start looking at them from the perspective of changing them from English into conditional statements. Their truth tables, though, should be pretty straightforward. Okay? You really don't want to think about or spend too much time thinking about why this is the case when you're just doing simple symbolic logic. Instead, you want to utilize the rules, okay? And utilize the rules in order to actually fill out your truth tables. So what we're going to do is we're going to start out with the first conditional, and this is the one we say P implies Q, okay? So we'll fill out our truth table. It's true, true, false, false here for P, and so that's P, excuse me. And then for Q, it's true, false, true, false. So when we say P implies Q, all right, what we want to get is first that when P, this thing here, okay, which we call the condition, P is called the condition, it's the first part. And then we'll have Q, Q is called our conclusion, and that's the second part. Okay? It's the second. Comes after the arrow here. And so if P is true, the first part is true, and Q is false, the second part, then what we have, is true, then we have a true statement. Great. Now, if our condition, P is true, but our conclusion, the second part is false, then the rules of logic tell us that that is in fact going to be false. If P, the condition is false, but the conclusion is true, then we're going to get a true statement. And if both are false, the condition is false and the conclusion is false, we're also going to get a true statement. So what we're going to be looking at is we're going to be determining which one's our condition, which one's going to be our conclusion, okay, or hypothesis conclusion, you'll sometimes see it. And so if P, right, is our, or if our condition is false, right, then it doesn't actually matter what our conclusion is. It can be true or false. We're going to always be getting a true statement. The only time we're going to get a false statement for our conditional is when our condition is true and our conclusion is false. All right. So now we have a set of logical constructions, right, that are all conditional as well. They utilize this conditional construction, but they're somewhat different, okay? So the first one we're going to look at is the converse, and that's where we switch P and Q, where Q becomes the condition and P becomes the conclusion. In this case, we're going to set up true, true, false, false. We're going to set up our false, false, excuse me, our truth table the same way. And now we notice Q is going to come first. All right. So when Q's first, Q is the condition, true. P is the condition, true. Okay, then that's true. If Q is false, condition false, conclusion true, that's now actually going to be true, right? That's kind of the same as this part of the original conditional. Now, when we look, if the condition is true, but the conclusion is false, that's going to be false, which is the same as this relationship right here. And then false, false, okay? False, false, we get true. And that's our converse. So that's what happens when we switch our propositions. Next up, let's look at our inverse, okay? So our inverse is when what we do is we're going to negate the condition, okay, and negate the conclusion, but the order is going to remain the same. So now we're going to have true, true, false, false, true, false, true, false. That's how I'm going to set up my truth table. And now the next piece that I'm going to do here is I'm actually going to do my negations first. And what you're going to see is that when we do truth tables, doing each part of our symbolic logic atomically, like one piece after the other, okay, and then doing them all combined all together is really going to help us keep orderly, and it's going to keep our conclusions straight. It's going to help us prevent us from making mistakes. So what I'm going to do now is I'm going to take not P. Well, if P is true, not P is false. Okay. Again, P is true, so not P is false. P is false, so not P is true. P is false, so not P is true. Right? Those are just the negations, the ones that we just did. Then we go to Q. So Q is true, so not Q in this case, along this line is going to be true. Is going to be false. Pardon me. Switch that. Q is false, so we switch it now, it's going to be true. Q for the third line is true, so that makes its negation false. And then we have Q being false, so that means its negation is true. Okay? Now, what we're going to do, if you notice, this conditional here, okay, is only going to use not P and not Q. It doesn't actually use P and Q. So we're only going to focus in on the not P section and the not Q section, not the P and Q. Those are going to be the values that we choose for our for determining the conditional. So I got false implies false. All right, so that's the false we're looking at. That's the false we're looking at. And when we have that in our condition, right, look back to our original conditional, that's actually going to end up being true. Next up, we're going to take P is false and not Q is true. Excuse me, not P is false and not Q is true. So when we apply it to our conditional, right, that's going to end up being true, right? It's this one right here, the third one down on our original conditional. Next up, we're going to look at not P is true and not Q is false. When we have that condition, when the condition is true and the conclusion is false, what we end up getting is we end up getting false. And finally, we have not P is true and not Q is true, and with our conditionals, that's going to end up being true. So there you go. Okay. Notice a couple of things that we got here. One is that we did the negations first, and then we figured out the conditional. And two, we actually, instead of using P and Q, we used our not P and not Q to determine the truth of our conditional statement. Let's look at another one, and this one's now called the contrapositive. And it's very similar to both the inverse and the converse. It's kind of both of those put together. And what's going to happen is that we're going to, what we say is we'll negate P and we'll negate Q, and then we're going to switch their order in the implication. All right? So we have P, true, true, false, false. Q is true, false, true, false. And now what we'll do is we'll say, okay, we're now going to change not P. Well, P was true, so not P is false. P is true, so not P is false. P is false, so true, and then true. And we'll do the same thing with Q. Not Q is now going to be false. Not Q in this case is going to be true because it's false here. Then we have true, false, false, true. And so what we've done now is we've actually set up all of our negation. Now we want to remember this, not Q is the hypothesis or the condition, and not P is the conclusion. False, false gives me true on conditionals. True, false now, though, gives me false, right? Remember, if the hypothesis is true and the conclusion is false, that's false. Then we get false, true, that actually ends up being true, and true, true, that ends up being true. And those are our truth tables for what we call our conditionals. A special group of conditionals is called the biconditional. And we're going to write this as P, and it's going to be stated as if and only if Q. So P if and only if Q. And P if and only if Q is actually what we'd say it's equivalent, right? Meaning it's exactly the same as P implies Q and Q implies P. So essentially what it's saying is that P if and only if Q is only going to be true when P implies Q is true and Q implies P is true. So let's actually set up a truth table for doing this, okay? And we're going to practice that like more granular approach to putting together a truth table. So we have P, we have Q. All right, and I only need 4 of these, so we'll stop there. So we've got true, true, false, false, true, false, true, false. And we'll notice I've got P implies Q. Okay, so P implies Q is one of our statements. And then we'll also have Q implies P. That's the next one. And so we'll have to do both of those. So first we start with true, true. P implies Q, that's going to be true. We know true, false is going to be false, then true, then true. That's from our conditional table. This is the converse, so we can use the converse table, which is actually true, true, false, true. And then what we need now is we need the last piece here, which we're going to use this equivalent statement, the and. So we're going to get P implies Q and Q implies P. Okay? And so what we'll do is now we'll use the and notice, since we've already figured out the values for the conditionals, we're only going to use the conditionals to determine the truth of this statement. So we got true and true, that's going to be true. One false, false and true is actually false when we're using the and. Remember, you need both to be true in order for an and to be true. True and false, that's going to be false. And true, that's going to be true. So when we look at a biconditional, okay, biconditional is only going to be true when P and Q are both true or when P and Q are both false. If they do not agree in terms of their truth, then the biconditional is actually going to be false. Now that we kind of have our granular or basic compound propositions, we understand our very atomic the standard propositions, which are very atomic, we kind of need an order of operations, right? In what order do we do things if we are not given, some kind of sequence? So the first thing that we want to always do is we want to do anything that's in parentheses. And so if something's in parentheses, then we're going to follow a certain subset, or we're going to follow what the order of operations is after that, but we're going to always do parentheses first. Okay? Second, we're going to do negation. Okay, so that's our negation. Negations are always done second. Third, we're going to do and. Fourth, we're going to do or. And then fifth, we're going to do our implication. Okay? So this is our and, this is our or, and this is the implication. In general, if you're writing symbolic logic, what we want to do is we want to actually demarcate utilizing parentheses in order to say what it is that we want to do done first. Although oftentimes what you'll see is like ands and ors, those compound propositions, separated by implications, and we just know that you're supposed to do the ands and ors first. In general, when you're going out and you're writing symbolic logic or you're trying to explain symbolic logic, the best thing for you to do is just use the parentheses. Use the parentheses because what it'll do is it'll make it a lot easier to work, okay? And it'll be a lot easier for people to understand what it is that you're trying to do. By the way, if it should happen that we have any of these that are, say for example, we have multiple ands, multiple ors, or multiple implications, what we should do is we move from left to right, just like we read. Okay? So if there are more than one of each one of these symbols inside of your symbolic logic, then we're going to actually move from left to right. Okay? So do the things on the left first and then move over towards the right. So there's our order of operations when it comes to doing symbolic logic. So now let's take a look at what happens when we have something that's a bit more complex. And so we'll start out with something where we've actually got three propositions, P, Q, and R. All right, so this is going to change the number of lines that we have in our truth table. And in addition to that, what you'll see is you got P and Q. In my case, I put them into parentheses. All right, and they are going to be together, going to be the hypothesis or the condition for this conditional, the one that implies R. So what I want you to do is I want you to follow along in terms of the order. I'm going to follow along with order of operations in terms of evaluating the truth for each part of the statement. And then that's going to allow me to really very smoothly figure out the truth of the statement overall. So the first thing I'm going to notice is that I've got P, Q, and R as my propositions. And when that's the case, instead of having four choices, right? Because P and Q, you've got two choices for each, and what we do is we take 2 times 2, that's 4. We now have 3 choices, so it's going to be 2 times 2 times 2, so that's 8. Okay, so we have 8 truth values, or truth values for P, Q, and R. If I had had 4, then I would have 16 different values for P, Q, R, and say S. If I have 5, P, Q, R, S, and T, what I'm going to end up having is 2 to the 5th, or 32 different total truth values, and my truth tables would quickly become very, very large. All right, so in general, we're only going to use truth tables for evaluating, say, for example, things that might have between 2 and 4 different propositions. So here we go. This is 1, 2, 3, 4, 5, 6, 7, 8. All right, now I've got P, I have Q, I have R. I will now set up my truth values. We'll get to this in a second. I'm going to set up my truth values for P, Q, and R. And so there's a pretty good method that we have for actually making this pretty simple. So here's P, here's Q, here's R. So I'm going to make the first half, so the first 4 in this case, I'm going to make them all true for P, and I'll make the second 4 all false. Makes sense that half are going to be true, half are going to be false. Then what I'm going to do is I'm going to say, okay, for Q, I'm going to go true, true, false, false. So 4 divided by 2, that's going to be 2. So every 2, I'm going to switch from true to false. False, false. So that gives me true, true, false, false, true, true, false, false. And then R, just like we did with Q before, we're going to do true, false, true, false, true, false, true, false. Okay? So we'll just separate every other one. Your last proposition will always look like that. It'll always switch between true and false. You can go and check, and I want you to check. That's going to be every single possible combination of true and false that we can have for P, Q, and R. Okay? Now the next thing I want to do is I want to actually represent inside of my truth table what I could have for P and Q, because that's what I've got to do next, right? In the order of operations, I've got to do whatever is in the parentheses. So that's going to be my next one. That's going to be P and Q. And then finally, once I figured out what P and Q are, I'm then going to use that in terms of the conditional for R. So I'm going to get P and Q in parentheses implies R. Okay? Now, what I know is I can go through and I can figure out the truth for P and Q using the P and Q truth table. So remember, P and Q is only true if both P and Q are true. And that's only going to be the case here, right? True, true, and the true, true for the first 2. And everything after that has a false for either P or Q. And so consequently, the last 6 values are going to be false. So true, true for the first 2. That's my P and Q. And then false, false for everything else after that, because at least one of the P or Q is going to be false. Now, for this next line, P and Q implies R, what I need to do is I need to actually use the conditional table, and I'm going to use the conditional table with my hypothesis or my condition being P and Q. I'm not even going to look at the original P and Q. So these two, you pretend they don't exist. So pretend they don't exist. All right? So my condition is my P and Q, and my conclusion is R. Okay? So true, true, that gives me true with the conditional. True, false, that's going to be false. False, true, that's actually true. Okay, remember, if the condition in the conditional is false, then automatically the entire conditional statement is true. So that actually gives me true. False, true is true. False, false is true. False, true is true. And false, false is true. And that completes our truth table. So given the values for P, Q, and R, P and Q implies R will have these truth values here. Key point here, very important, is to notice that what we have is we did P and Q first because that was first in the order of operations, and then we did the conditional. Once we did P and Q, we ignored the original P, Q propositions because we'd already used them in order to create our compound proposition. So let's look at another example. Let's suppose that we have this one. Not P implies Q or R. Okay? So what we want to do is we want to figure out when is this statement going to end up being true. So we got P, Q, and R. So that means that we're going to end up having 8 different lines inside of our truth table. P, Q, R. And we'll start out, we got true, 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 false, 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 false for P. Then Q will give me true, true, false, false, true, true, false, false. And R will give me true, false, true, false, true, false, true, false. And those are our values for P, Q, and R. Notice next what we're going to do is we're going to do this conditional. We're going to do P implies Q next. And we're going to do P implies Q because that's the one in the parentheses. So we're always going to use our order of operations to tell us what is it that we should do next inside of the truth table. So now P implies Q, conditional, I get true, true. This will be false and false, right? Because if you notice, P, true implies false is false. True implies false again, that's false. And then the rest of these, because if the condition is false, the conditional is always true, we end up with true, 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 true. Okay? Now, what's next is we're going to have to go through and negate each one of those. So I'm going to go in and I'm going to write my next term is actually going to be the negation of P implies Q. And so that should be pretty simple. We just write the exact opposite of whatever's here in the P implies Q. So that's false, false, true, true, false, 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 false. And that's the way that works. Now that we've done that, we can go in and we can do the OR statement right here. Because that's the last piece that we need. So we've got not P implies Q or R. And so we'll look. If R is true, then remember that for the inclusive OR, right, only one or the other of our statements actually has to be true. So if R is true, the whole statement is going to end up being true. So I'm just going to go true. Okay, true, true, true. That's because each one of these R's is true. I only need one to be true, so each R is true. That's great. And now I'm going to go to the not P or Q. Well, This is false now, so that should be false and false. You can see that. That's going to be false. Okay. Here I've got a true for not PRQ, so that should be true. I've got a false, so that's false, false. That's false for the whole statement. And then for this last value, false and false, we end up with false as well. Okay. So again, just something to notice here is once I've actually set up my truth table, all right, I'm going to work utilizing the order of operations to determine the truth of each compound proposition that's part of my larger compound proposition. All right. And at each step along the way, I stop looking at the stuff that I was using before and only look at what's necessary inside of that compound proposition. All right. So this completes our introduction to symbolic logic and truth tables. Hopefully it makes sense what it is that we're doing. I want you to be very cognizant that the best thing you can do is to memorize the truth tables, right? Memorize the truth tables and then memorize the order of operations so you can work through the process. And then after that, everything else gets much easier to do. You don't want to actually be thinking about, right, whether or not something's logical or not. In general, we as human beings are not very logical. And I include myself in that. Right? We are generally not very logical. Instead, we want to focus on utilizing the rules of logic and following those rules of logic, okay? And that will not steer you wrong whenever you're doing symbolic logic.